All right, I want to use the theorem that we just did, the equivalent statements theorem, to find a way to calculate inverses. And what I'm going to use is that the statement A is invertible is equivalent to the reduced row echelon form of A is the identity matrix. So this thing right here, that the reduced row echelon form is the identity matrix, is telling me that if I start with A, there is a sequence of row operations that will get me to the identity matrix. So rather than just saying I'm going to do some row operations, I'm going to represent each of those as an elementary, multiplying by an elementary matrix. So there's some sequence, E1, E2, all the way up to EK, that correspond to row operations that you're applying to A, with the end result being the identity matrix. Okay. Now notice that what I have here is a product of something times A equals the identity. So this something right here, this stuff, has to be the net total being A inverse. So what I have now is that A inverse is actually equal to this product. Sorry, EK, please. EK down to E2, E1 is A inverse. I'm going to add on just one, not add on, but sort of multiply on an identity matrix here just on the end, just because it doesn't, multiplying by the identity matrix doesn't change anything. But what it does do for me is it lets me see what these row operations do to a different matrix. If I do these row operations to A, I turn it into the identity matrix. But if I do the same row operations, E1, E2 up to EK, on the identity matrix, it turns it into A inverse, which leads to us doing something like this. Make a big matrix. Take matrix A and stick next to it. Those are just dots, just indicating that I'm doing more stuff. Put an identity matrix next to it, and then put it into reduced row echelon form. Well, the row operations that you're going to need to do to put it in reduced row echelon form are the things you're going to need to turn A into the identity matrix, namely these row operations. If I do those row operations on this big matrix, A will be turned into the identity matrix, and the identity matrix will be turned into A inverse. Okay. So let's do an example here. Now I'm going to do a 2 by 2 example where we probably already know the answer, right? Because we have a method for doing 2 by 2s. But let's, sorry. Let's let A equal 2, 3, so that 2, 1, 5, 3. Okay. So what I'm going to do is I'm going to make this matrix here 2, 1, 5, 3, 1, 0, 0, 1. So I've got the matrix A in the first two columns, and I've got the 2 by 2 identity matrix in the third and the fourth column. So then I'm going to do some row operations. First thing I want to do is there's a lot of different things, different ways you could do it, but I'm going to swap the rows. 5, 3, 0, 1, 2, 1, 1, 0. The reason I'm doing this is because I didn't want to introduce fractions. So what I'm going to do now is I'm going to replace row 1 by row 1 minus 2 times row 2. So row 1 minus 2 times row 2. And so that would be 5 minus 4. 5 minus 4 is not 0, it's 1. That would be 3 minus 2. That would be 0 minus 2. And 1 minus 0, 0. This I'm still leaving alone. Then the next thing I'm going to do is I'm going to replace row 2 by row 2 minus 2 times row 1. So row 1 is staying the same. And so I've got 2 minus 2. I've got 1 minus 2. I've got 1 minus negative 4. So 1 plus 4 is 5. And I've got, uh-oh, what happened here? I think I made a mistake right there. This was supposed to be row 1 minus 2. So this is 1 minus 0, which is 1. You probably already caught that. So here we are. There's a 1 right there. So is this one probably wrong? Let me try this again. So this is row, no, this one was left alone. Yeah, so that's a 1. And then I have row 2 minus 2 times row 1. So that should be a negative 2, I think. Here we go. Next thing I'm going to do is I'm going to multiply the bottom row by negative 1. So negative 1 times row 2. So 1, 1, negative 2, 1. Hopefully I can get this right. 0, 1, negative 5, 2. And then I'm going to get a 0 right here. So I'm going to replace row 1 by row 1 minus row 2. Okay. So here we go. 1 minus 0, 1 minus 1, negative 2 minus negative 5. So negative 2 plus 5, so I'm going to put a 3 right here. I said 3. And 1 minus 2 is minus 1. And then I've got a 0, 1, negative 5, 2. So I'm now in reduced row echelon form. Notice I have an identity matrix here because matrix A, reduced row echelon form, was that. And what's over here is should be A inverse. So A inverse, I'm claiming, is 3 minus 1 minus 5, 2. Is it? Notice these two got swapped. Right? The 3 and the 2 got swapped. You got minus signs in front of the 1 and 5 now. And the AD minus BC, 6 minus 5 is 1. So I did multiply by 1 over 1 out in front, and I do actually have the inverse. Okay, so this works on any size square matrix, so as big as you want. I would point out that you don't have to do these all by hand because your calculator can do them. Just type in if this is n by n, then this is going to be n by 2n, and type A into the left side and identity matrix into the right side. As for reduced row echelon form, you should get an identity over here and A inverse on the other side. Okay. This is a method of doing this, of calculating inverses, which comes from knowing that A invertible is equivalent to the reduced row echelon form being IN. And that sequence of row operations that takes A to the identity will also take the identity to A inverse. Okay? So you just do them all at the same time, and you get the inverse.